closures and barrel comparator. I'm a reporter from Chinton High School. Today I'm going to report the problem 15 of my school. And here is the problem statement. Generally press a piece of tracking paper on the surface of water. It rapidly curls into a screw and then slowly uncurls. Explain and investigate this phenomenon. And our main focus was on the property of the tracking paper and which properties are relevant to this effect. And the curl up when pressed on the water as described. And here is our outline. And here comes to the observation video. And here we can look at the observation video. The tracking paper will curl like this. And here is the theory. And we first talk about the tracking paper and why we use the tracking paper. And because it has the expansion is significant. And the slow water absorption rate, and because it has the different expansion of the paper. And here is the thermocycles. And we explain the tracking paper for two layers. And here is the upper layer, and here is the lower layer. And when the tracking paper contains the water, and the lower layer will expand. And the P2 is the force, and because the lower layer will expand, and the upper layer won't expand. But it's the same paper. So the P will, the direction will like this, and the P1 direction will like this. And here is, we will do to the force equilibrium. And M1 is this, and M2 is this. And due to the force equilibrium, we will know that P1 will equal to P2 and equal to P. And M1 plus M2 will like this. And here is the visceral rigidity of the layer above. And here, because we have the upper layer and the lower layer, but it's the same paper, so the expansion will be the same. And we can get this equation. And here we will image the upper layer and the lower layer to be two different metals. And the upper layer and the lower layer, it has a different expansion coefficient. So the lower layer will curl up to the upper layer. And here is our quotient of the K. Then we can get the curvature over here. And here is we will let the N to be this and N will be this. And we will need to also remember the I1 and I2, the last stage we talked about. And here we can put the N and N into this quotient so we can get the curvature over here. And here we will come to the molecular diffusion. And the molecular diffusion is about water absorbed into the paper. Because the molecule is different, so the water will get into the lower layer of the paper. And here we'll describe the west layer thickness over here. And here's our model. And we will combine the two theories. So our curvature will like this. And here the kappa has a maximum, and here it will be the 1.5, and when the t, we assume that it will be the Tn, and the n will be 1. And if you can get this 1.5, and the equation, okay. And here it comes to the spontaneous symmetry bracket. And because the tracking paper, it will be like, you will have the fiber like this. A paper, you will have a fiber like this. So it will cure like this, it won't cure like this. Because the expansion coefficient is different. The expansion coefficient like this is bigger than this. And here is our experimentation. And this spontaneous symmetry bracket. And we use a different paper type. And we will know that the bigger expansion is like this. And the smaller expansion is like this. And here is our video. You will see it won't depend on the paper shape, and it will depend on the fiber direction. And here is the ocular diffusion. Here, why we use the ocular diffusion is because we can look over here, and the water and the water-rich soap. And the capillary action is not the main reason that causes the paper cure, because the soap capillary is not the same as the water, but our data is very similar. And here is our express step. And first we will cast a rectangular piece of paper to test the cure direction, and then we'll cut 3 different sections of paper into a 2x2 square. And we will take a video until the paper is completely unfolded, and we will take a video to its complete cure, but not the action before the complete cure, because the tracking paper will be flat after it absorbs too much water. And the first step is extract and analyze the curvature change through the video. And the first variable is thickness, and we also only have one variable. And here is our graph of this is thickness squares, and here is the time. And we can know the thickness square and the time will be the linear. And we can also prove the ocular diffusion is correct. And here is we use different thickness, and we can know the bigger thickness will need a longer time to get through the cures. And here is a curvature time square. And the line is our models. And this we will use T and K to normalize the data, and we can compare different type of the paper thickness. And we can know that the different type of thickness is similar. But at the front pass, it won't like the model because of the surface tensions will push down the paper to be cured. But it's not the reason that cause the paper absorb the water. And here's my conclusion. The surface tensions won't affect the velocity of the tracking paper absorb the water. It will only affect the tracking paper at the first of its curl. And the thickness of the tracking paper increase the time the paper curl to the maximum curvature increase. We can prove that in our experiment. And the paper will curl at the same direction because the expansion coefficient has huge difference in two directions. Thanks for your listening.
I would like to ask you, how did you observe the orientation of fibers?
Observe.
The direction of the fibers.
We use the camera to take a picture and look at the fiber direction.
And is diffusion equal to capillarity?
No.
Okay. And is the curvature mentioned in your experiment 3-dimension or 2-dimension? 2-dimension. Okay. And so why it would expand? Is it the material or the shear force?
Because the paper absorbs the water and the bottom.
Okay. And you mentioned that the molecules are different in your presentation, and why are they different? The molecular parts. Okay, that's okay. And in page 10, you mentioned that the expansion of 2 layers of the paper are the same. And
yes.
Okay. And do you consider the influence of temperature in your experiment?
No.
Okay. That's it. into opposing problem 15. Let's scroll. And here's the problem statement. If we gently place a piece of tracing paper on the surface of the water, it rapidly curls into a scroll and then slowly uncurls. Explain and investigate this phenomenon. And the reporter's focus was on discussing the relevant parameters and explaining the phenomenon. So here's a summary of the report. For the phenomenon, the tracing paper will curl and uncurl at a different expansion rate. And here's the theory. Tracing paper and the tracing paper absorbed the water at a slow rate. And they used Timoshenko's bimetal thermostats model. And also they mentioned molecular diffusion and spontaneous symmetry tracing. And also for the experiment, they conduct experiments about paper type, surface tension, and paper thickness. So here's the pros and cons of the report. For the pros, they clearly demonstrated their theory, and they compared the curvature in two different directions, and also they had thorough explanation of the formulas. Also, they clearly explained the graph for the model. And for the cons, they lack of this discussion in the phenomenon, and also they lack experiment setups. And there are errors produced by manual operation in the experiment since they place the tracing paper by their hands. And also they lack of information about how they conduct the experiments. And there are too less experimental data in some sets of experiments, and we consider it not complete. And during the discussion later, we are going to focus on relation between diffusion and capillarity between, for the theory. And for the phenomenon, we are going to discuss the expansion. And for other topics, we're going to discuss the fiber orientation, the temperature, and dimension of curvature. So I would like to invite the reporter. So first, you mentioned, like I just asked you, you mentioned that the expansion of the two layers are the same.
Yes.
However, in the later statements, you said that the curling was caused by the different expansion. So doesn't it contradict between your statements?
Because the lower layer will absorb the water, but the upper layer won't. So the expansion is different, but it's contained to the same paper. So in our theory, we have to since that be the same paper.
So why did you said that the expansion are the same during the questioning?
Because it's the same paper.
Okay. And so according to the problem statement, the tracing paper will curl fast and uncurl at a slower rate. So how do you explain this phenomenon?
Because we can see the data over here, and when the cure has to open, can we use the method? Parameter is pure, we made like this. And the content area will only here. But if a flat paper goes to this, it has
So your main focus is on the content area of the paper in the water.
of your question.
Okay.
It's because of
And you mentioned that you observed the orientation of fiber by using the camera. So are there any evidence or pictures that you can show us the orientation of the fiber, or the direction?
maybe we only can look at the picture to nose and the fiber direction is like this. And also maybe we can have another solution is that after the paper is pure and we can take out the paper to know the fiber.
So have you tried to use devices like microscope or some magnifying device to prove your theory? I mean, have you used microscope to observe the thing for
fiber?
Yes.
Yes.
So are all the fibers in the same direction, or there are actually some of the fibers in a different direction?
Tracking paper fiber would be like this. But the expansion of here is bigger and the expansion over here is very, very
So
small.
how can you explain this phenomenon? You mentioned that the main cause of this is diffusion of water molecules. Is that correct?
Yes.
So how can you explain this? Why will the paper expand more in one direction?
More in one direction. Because maybe we can look over here, and the water when it expands, it may like this because the lower layer it may have more water.
I mean, why will the expansion on this direction more than this direction?
Because we have because the fiber.
I know the
Because the
origin of
coefficient.
fiber.
Because the coefficient is different.
So where does the coefficient come from?
Come from fiber or what is it?
So maybe I think you can try to use water which has color or ink in it, and you can observe the process of the diffusion.
So you mean that the water absorbed into the paper, so the paper will maybe here will contain the color water, so it will be pure, so I can observe.
Yes, since the water there's no color of water, and you can't actually observe the phenomenon.
But I have a question. Is that because we look at the distillation version and the thickness is very, very small, about 60 μm.
Yes.
But how can I look at know the?
I mean, since there are fibers and the materials of the fiber and other parts of the paper may not be the same. So there might be a different diffusion phenomenon of water. Okay, so let's move on to the next question. So during your experiment, you just put the tracing paper in the water fiber can. So do you consider the manual error in during this
Because this
experiment?
is the observation video, but we use the clip to make sure the consent area at first is the same.
So how can you make sure that every time you place the tracing paper on the surface of water and the paper and the surface are always parallel, since you still place it by your hand, even though you use a needle or something.
You mean the?
I mean, how can you make sure that you can decrease the manual errors?
I think maybe I can draw the line to make sure.
Okay, and so in this part, I suggest that you can try to use some mechanical device such as robot's arms or something to conduct the experiment. And since during the questioning part, and I asked you if the curvature in your experiment is 2-dimension or 3-dimension, and the answer is 2-dimension.
Yeah.
However, you mentioned that there is an expansion on both x and y axis.
Yeah.
So why can't you just calculate the curvature in 2-dimension?
Because of the expansion, we have a mixture, the expansion of different direction, but we can surely measure this direction's expansion. So in our theory, we use the 2-dimension.
So why did you try to use the 3-dimension curvature to make sure that your theory is complete, your experimental data are complete? Maybe you can try to use 3-dimension, and we'll move on. Can you elaborate on the ratio and distribution of the 2 layers? Are there any actual data or experimental results?
No.
Okay, and maybe you
Because
have
we can use the mixture to know the expansion difference as a maximum.
So where does the pressure come from?
Pressure. You said the pure pressure.
Yes, pure pressure.
It comes from the lower layer. Because the lower layer has more water and pure
Okay.
through the neck.
And let's move on to your experiment results. And we can just see there are just few parameters that you conduct in your experiments. And
Yes. We have done different shape. Here we use two square, but we also have done like 4 square or x square, but the time is the same. So we use the 2 square. It has more auxiliary to measure.
Okay, so did you change the paper, or do you use the same paper with the different area?
The paper, we just cut the shape. We don't have
Okay, and so can you explain why, the time span of the curling of the paper will be the same even though there are different areas?
You said this picture?
Yes.
This is the normalized data because we have to compare different thickness paper. So we use the normalized data or the different thickness data will like this.
Okay, and so I suggest you to conduct more about the experiments because the parameters are a bit less. So here's a summary of the discussion. And first, we discussed about why the paper curls fast and uncurls slow. And I think they lack of explanation in this part. And we also discussed about fiber orientation, and they failed to explain. And I think they should try to use precise equipment like a microscope to observe it. And also for the experiment, we think it's inaccurate due to manual operation. And the relationship between the diffusion and capillarity, the experiment actually contradicts the theory. And also the dimension of curvature, and they failed to discover the curve in y-axis. Also, the different ratio of tracing paper, and I think they failed to consider it. Also, they lack of parameters.
So there are a few questions. First, I want to ask the reporter why the paper finally be flat.
Because the paper, we know that lower layer will absorb the water, it will be pure, but because of the time, the upper layer will also absorb the water.
Also, it will also expand.
And because the expansion is the same,
Yeah.
so it will be flat.
So that question is for both the reporter and the opponent. So do you think the fiber will expand vertically?
You mean?
In your experiment, you only like the dimension only about yes it is. And what about the vertical?
It may, but we think it's negligible.
So it's negligible. Okay. So what kind of do you think the overlap will affect your experiment? In your experiment, what kind of how do you define the curvature?
Curvature.
Can you use the whiteboard? Jeremy, can you use the whiteboard? Yes, thank you. So in your experiment, what kind of expand will be like? Is this?
This.
So it won't look like this.
Won't.
Well, it won't look like this. So how do you define the curvature? Is the curvature of here? Okay. So it's like you mentioned in your experiment, the thickness of the paper won't affect the final curvature, right?
You said thickness.
Thickness.
Um,
The final curvature are the same, right?
You don't measure the final texture, but I think it won't be the same.
It won't be the same, but in your chart they are all the same. The final curvature in the previous page. So do you think that is there a boundary that the curvature are all the same, or is there
Yes.
there's a boundary? And what about you? Do you think there's a boundary that the thickness won't affect the curvature?
Actually, thickness only affects the duration of time of the curling instead of the curvature.
So do you think there's a boundary like very thick that the water cannot absorb?
Of course, but actually, we don't consider it during our experiments since there's not that big of a field.
Okay. What about, do you think the when the paper sink into the water will affect? When the paper sink into the water, will it affect the whole process?
Yes.
Then
Because it has different layers.
Now iteration review.
so I'm going to review the question about the wet scroll. And my name is Alex. And this is the problem statement I think you have seen before, so I just cut through it. And these are theory details. Tomaszenko by mental Fermat's model to describe their theory and the different expansion speed, the force equivalent. As for the parameter, they try different tracing paper and different surface tension and thickness of the paper. As a strength, they are good at modeling of the theory and the graphs to explain the theory. As for the suggest, I think they can get more parameters and there are more explanation of the theory and then the explanation of the data, and the data is a little bit split. And as for the discussion topic, the opponent asked how do you observe the direction of the curve, and the reporter replied that I took pictures to know it, and I think taking pictures is the way that know it, and you can analyze it from the like image shaping and then analyze the curvature. And as the opponent asked, did you consider the temperature in the experiment? And the reporter said, no, we don't. And I think temperature is not important in this experiment because maybe the rate of the temperature won't affect very much. And as for opponent asked, why did you set up the expenditure the same? And reporters say that because the same paper, I think this answer I don't get satisfied because the rate of the expansion actually slow down by the water get higher and higher. And upon asked why will the expansion direction will impact the results, and the reporter replied because the coefficients are different, so it's caused by fiber. And I agree with the reporter. Next, opponent asked how do you make sure your paper put out water the same in different experiments? And reporter replied, not sure. I think you have to make sure your theory will collapse. And the opponent suggests you can measure the contact angle. And the reporter replied, no reply. And I asked why the tracing paper will finally flat. And the reporter replied, the upper paper will also expand, so it will flat. So I agree with that. And reviewer question, I say, will the fiber will expand vertically? And reporter said it will be neglected. So I also think it will be neglected because in the experiment we are analyzing the two-dimensional expansion, not the three-dimensional. And the opponent also agreed with that. And I asked how did you define the curvature, and the reporter answered both sides with the picture right. And I asked, do you think the thickness will affect the boundary? And the reporter replied, it will affect the resolution. Oh, no, that's wrong, that's the previous one, sorry. And the opponent replied, the thickness only affects the duration. And I agree with that because that is not a pretty point. Thank you for your listening.
For reporter concluding remark from the opponents, and we discussed about the extension, and we discussed about QRS and orientation of the fiber, and we know that the fiber direction is the same. And the opponent raised a good setup about the discussion of the fiber expansion by association. We don't think manual operation will affect the apps. And from the reviewer, he definitions of the curvatures, and we discussed on the whiteboard. And the curvature was not be the same, and will not be the same final, and cause the model was elastic difference. Because you can think that if the paper have 5 centimeters thickness, and maybe its model was like this. And here's my concluding remark.
Right, some questions for Guru. guys will talk about the fiber, and then the opponent suggests that you can use the microscope to get the fiber. Is there any other way?
I think maybe we can look at the fiber after the experiment because the wax paper and we can spread into two pieces and look for.
I think you can use the weight because the fiber can actually get more weight. So if you give the weight at the fiber direction, the fiber direction actually can take more weight than if the fiber direction like this and you give the weight like this, it will crack more easily. The weight will be not much as the fiber direction.
I think we can use the microscope to observe the process of the curling so that we can make sure how the water diffused in the tracing paper.
Any other questions from the group? Please.
I want to ask a naive question to all three groups. I want to know, how do you think about the effect of the shape of the tracing paper?
I think it won't affect the result because we have the video over here and we know that the fiber direction. But though we use different shape of paper, it also comes to the same direction too.
I think you will curve the same directions. Yes. Curve the same directions, although the shape is different. The final, it will be like this. Yes.
So as long as the paper are the same, the paper pieces are cut from the same paper, and we think that the curvature and the whole phenomenon will be actually the same, and the shape won't actually affect the phenomenon.
Question? Please.
So for the opponent, you mentioned a phenomenon that it curls faster and it gets flattened again slower. So I would like to offer you, so what's the reason behind this thing in this technology?
During the discussion, we have talked about it, and we think it's because when the paper curls and when the paper curls, the contact area is larger, and also when it uncurls, the less water. Also, when it curls, less water are absorbed. So the speed will be faster.
I think it has two reasons, and the one reason is we talk about as over there, and another reason is because of the molecular diffusion. Because molecular diffusion depends on the different molecules, and the bigger molecule goes through the smaller molecule, it will be the faster. And we all know that at the beginning of the experiments, the lower layer contain the water, but the upper layer contain the wet lower layer. So speed will slow.
So I think it is something to do with the contact area with the water. So you see the faster that they curve to the final height, actually its curvature is bigger, so the contact area with the water will be less. Yes, sir. Yes, sir. We are still alive. We're not dead.
Right, so during skips our score to the recorder. 6, 5, 7, 5, 6. The score for opponent. 7, 7, 7, 7, 7. The score for reviewer. 6, 7, 6, 7, 7. Right, thank you everyone.
Yeah.